Good morning, friends. It gives me immense happiness and joy to be here again for my course, Thermodynamics, that is Engineering Thermodynamics. I am now starting my module number 4, and the name of this module number 4 is Thermodynamic Power Cycles. We know that the engines, let it be petrol engine, diesel engine or gas turbine or any power plant, these mechanical devices are operated by the thermodynamic processes, thermodynamic cycles. As of now, we have seen that the Carnot cycle, which is producing the maximum efficiency for a given range of source and the sink temperatures. But in the real case, finding the Carnot efficiency is very difficult because it contains all the reversible adiabatic cycles. So finding the reversible adiabatic cycle is impossible. So the Carnot cycle has become an ideal as the reference cycle where we can compare our work with the help of Carnot cycle. Here in this, we are going to discuss in this module the 5 cycles. First one is AutoCycle, second one is the diesel cycle, third one is the dual cycle, fourth one is a Brayton or Joule cycle, and the fifth one is Bell-Coleman cycle. So these 5 cycles we will be discussing. First 3 cycles are the closed system or the control mass system we have to apply, and for the last 2, that is Brayton and the Joule cycle plus Bell-Coleman cycle, they are the control volume system because the mass is not constrained in a given space. Mass will change its boundary. So these things will be discussing in this module. We will be also discussing about number of numericals on AutoCycle, diesel cycle and some other cycles we will be handling, and hope this will be very useful for all the students, those who want to learn the thermodynamic cycles. So in today's class, I am going to discuss about power cycle, Rankine cycle, introduction to internal combustion engine, introduction to AutoCycle, PV and the TS diagram for AutoCycle, thermal efficiency and applications. These topics I am going to take for today's lecture. As per the syllabus, we have these cycles. First one is AutoCycle, second one is the diesel cycle, then dual combustion cycle, description and representation on PV and the TS diagram, thermal efficiency, mean effective pressure on air standard basis, then comparison of cycles, then last is introduction to Brayton cycle and the Bell-Coleman cycle. So these are the 5 cycles which I have already told you that these, and as per our syllabus also, these cycles are given. So I will be focusing on this. However, in between some basic cycle also I am going to cover in this next slides. So we have seen in our previous discussion that about second law of thermodynamics. So from this, if you see the first law, so first law says that del Q is equal to del W. Delta Q is equal to delta W. It means whatever heat you supply, it will be converted to the work, or if you give some work, this work may be converted to the heat. So heat and work both are the interchangeable. We can say that the first law of thermodynamics is a conservation of energy. But in the real sense, these things are never happen. Whatever you give heat, all 100% of heat will not convert to the 100% of the work. In this case, the second law of thermodynamics was investigated by Kelvin Planck. They have given their statement, and they told that if you take any reversible engine, there may not be 100%, but there will be some losses. Heat cannot be transferred from a lower temperature to higher temperature instantaneously. We need to give some work, and there are some entropy losses. This entropy will be generated, and this generation of entropy will give the losses of the given energy. So the total energy will not be able to convert to the work. So here one word has come that is called eta, and this is called efficiency. So here, if you see that I have just discussed about Carnot cycle. This Carnot cycle, if you draw, it is an isentropic process, PV diagram. Then this is the isothermal, again isentropic, and again it is a 1, 2, 3 and 4. So this 1 and 2, they are the S is equal to constant, and this temperature is constant. So we have here two processes, and all processes 1 to 2, 2 to 3, 3 to 4, 4 to 1, all are the reversible adiabatic process, and it means here entropy remains constant. Entropy remains constant means change of entropy delta S will be 0. This is the condition for this ideal cycle. But in the real sense, we are everywhere there will be the S generation. This generation will be always positive for any system or anywhere you heat and work is interacting, and you are getting the power by the help of the heat, or you are generating heat by the help of the work. So anything which you do, there will be some losses, and these losses are defined with the help of efficiency. Okay, so this we are going to make the real in this chapter. We are going to discuss about some new cycles. In that AutoCycle I will be discussing, and in this we are not following all this process of Carnot cycle. Here we are, in place of this, we are following heat addition at constant volume, but here it is a constant temperature. So these things we will be discussing in our. So what is a power cycle? A power cycle consists of a series of repeating thermodynamic processes along a closed process path while heat is converted into mechanical work. So in this there will be number of processes, and these processes will move from state 1 to state 2 to state 3, state 4, state 1 again, and they will make a cycle. Means you will move from one point and you will go from 1 to 2, 3, 4, 5, 6 and again 1. You have to come back to its original position from where you have started. So this type of processes, and during doing this we get some mechanical work. We invest some energy as a heat or heat energy. We can convert it from chemical like petrol or diesel or kerosene. We burn it, or any other fuel we burn it. That heat we have to utilize to get the work done. So that is the mechanical work we have to, from heat to the mechanical work we have to convert by the help of the power cycle. The most widespread working medium is water and air. So the power cycle involves the water's change of phase from a liquid state into a superheated steam. So if it is a water, we are using. So we have to convert this water into the steam, and from the steam, we have to convert to the superheated steam. The expanding steam performs work on its surrounding. So as and when this steam is expanding, this expansion may be inside the cylinder, or expansion may be in the turbine or anywhere. As and when we expand the gases, we get the work done. That is returned to its initial state, changing its phase into liquid. So during this expansion, initially we have compressed, then it is given some heat. By the giving the heat, it started evaporating. This evaporation start the expanding the gases. During the expansion, we get the work done. Again, it is cooled down during the expansion, and it again comes to its equilibrium, or again it's come to its original state. So in this way, one full process is completed. Such a cycle was invented by the Clausius and the Rankine, and is usually called the Clausius-Rankine cycle. This is the first basic cycle which was developed by Clausius and the Rankine. So this you can see here, the Rankine cycle, how it is there and how we can do it. So we can see here, I will start from 1 and 2. Here is the pump. This liquid from here 1, it is pumped, means it is pressurized, and this pressure goes to one boiler. So here it is heated, means heat is given. It may be the burning of fuel, burning of coal, burning of your wood, anything which you can heat it, this system. So from here, this cold air, cold water which was compressed by the pump, it is fed by this here. By the heat, it is heated. The heat is given Q in here by the help of any of the burning material, maybe petroleum product or the wood or coal or anything. So this is heated, and after this heating, the temperature of this water is increased slowly. This you can see the color as it goes up and up and up. This thing is increasing, and here it is very hot. The water has become very hot, and the water is slowly due to the heat start converting to the vapor, and at some time total water is converted to the heat, to the vapor, and it becomes a superheated steam. When there is no part of water in the steam, then it is called the superheated steam, and mostly we use the superheated steam. And this superheated steam goes to the turbine here, 3 entering and this 4 is leaving. So inside this we have got very hot vapor here, that is steam. This hot air is expanded, means here you see the volume is increasing. So here slowly this hot is slowly it is becoming the cool, and heat. Here it is very much cool. But still, if you see the color of this and color of this, it is violet and here is blue. Means still this is hotter than the input of this. So we have to use this little hot to, again we have to cool, and here we have to use your condenser or the radiator, it is called. So here cool water is entering here in this pipeline, and it is leaving, and the hot water and the vapor mixtures are leaving here, and this becomes again full water, and again these things are accumulated here. In this way your whole cycle is completed. So this type of cycle is called the Rankine cycle, and this is used for any power plant. We use such type of devices to generate the power. So here the turbine is in this vapors are expanded, and your turbine start rotating in this way, and the work is generated. And from here, if you connect the generator, then we can get, so we can get here the power here. So electric power we can generate by the help of this. And this is very old system. Nowadays, so many modifications are used in this type of system. So here the same thing is explained here by the help of this TS diagram here. So here we can see here that 1 and 2 here, very small part here, 1 and 2. So this 1, 2, the working fluid is pumped from low to high pressure. Okay, if you see the previous diagram here, this is the pump which is making from low pressure to high pressure, and here it is shown 1 and 2 here. This one, this part. Okay, so 1 and 2, the working fluid is pumped from low to high pressure, as the fluid is a liquid, and in this stage the pump requires little input energy. Process 1, 2 is an isentropic compression. So here if you see, it is a vertical line, it is a entropy. So here 1 to 2 is vertical line. Now 2 to 3. 2 to 3, the high pressure liquid enters a boiler where it is heated at a constant pressure by an external heat source to become a dry saturated vapor. The input energy requires can easily be calculated graphically using an entropy chart or enthalpy entropy chart, or by the molar diagram, or numerically using the steam table or software. Process 2, 3 is constant pressure heat addition. So here 2, and from 2 to 3, from here to here, it is a constant pressure heat addition. This you can see. This is the constant pressure heat addition. 2 to 3. So now we have reached to 3, and now this, if you see this diagram, so 1 to 2 here, then 2 to 3, it is in the boiler and steam is made. From 3 to 4, it is here adiabatic expansion will take place in the steam. So here process 3, 4, the dry saturated vapor expands through a turbine generating power. This decreases the temperature and pressure of the vapor, and some condensation may occur. The output in this process can be easily calculated using the chart of tables noted above. Process 3, 4 is an isentropic process. So if you see here, this 3 to 4 is a perpendicular line on this x-axis. So this indicates that this process, and this is the, here work is done. Work is extracted by the turbine. Last process is 4 to 1. This wet vapor then enters the condenser. I have shown this is the condenser here. This is the turbine. This is the pump, and this is the boiler. This all are represented in the Rankine cycle. So the wet vapor then enters a condenser where it is condensed at a constant pressure to become a saturated liquid. So here if you see, this process is 2 to 3 is a constant pressure, and 4 to 1 is also constant pressure process. So here it will become again saturated liquid up to 1, and it is full water is received on the pump. So we tell this as a pump. We cannot say as a compressor, because in the compressor we use the gas to compress, but the pumps are used to pressurize the water. So that is the difference between a compression and the pump. So process 4-1 is a constant pressure heat rejection in condenser. So this 4-1 is a constant pressure in the heat rejection in the condenser. So this Rankine cycle is completed. Hope you have understood. And this is the very basic process for any power generation of any system. Before I go for further explanation of any other cycle, that I will start with the AutoCycle. First, I will discuss what is the internal combustion engine and how these things are working. So, an internal combustion engine is a heat engine in which the combustion of a fuel occurs with an oxidizer in a combustion chamber. That is an ideal part of the working fluid. So here we have this engine. In an internal combustion engine, the expansion of the high temperature and high pressure gases are taking place. So here just I will explain first the part. So here we have the piston here. This is the piston, which is, then we have here crankshaft. This is the connecting rod here, R. This is the inlet valve. This is the exhaust valve. This is the spark plug. Okay, here are the vanes here to for the cooling. This is the water is circulating here, water. So I think all parts I have discussed, and this is the piston here. This part is cylinder, not piston. This part is cylinder. Okay, and this is the here piston, connecting rod. This is the crankshaft. So these are the parts of a piston engine. So I will try to explain the spark ignition engine. So because here spark plug is given, so I will discuss about the spark plug engine. So if you see here that from this I, initially the piston is at this is the top dead center, and at the last this is the bottom dead center, BDC. So initially your piston is at the top dead center. In this position all the valves are closed. As it start moving, so how it will start moving? Like manually you can crank it like your scooter, or nowadays we use the battery. The battery, there is a motor, it will rotate the initial. So initial rotation, it will go down. As it starts going down, this valve, that is inlet valve, is opened, and from here air and fuel mixture will enter, because it is a spark ignition engine. So air and fuel means air plus petrol will come from the carburetor, and here the carburetor is attached here, and from here it will go the mixture of air and the petrol. It will enter slowly. This valve will remain closed. In this, it is called suction stroke. So it is start going down. The here air and the fuel mixture is entered up to BDC here, and this full chamber is full of air and the fuel mixture. Now it will, from here, it will move upward like this. During motion, upward motion, here the air and fuel mixture will be compressed. This is called the compression stroke. Compression stroke. In this case, your inlet valve and exhaust valve both are closed. So the compression ratio is increased. For petrol engine, it is from 6 to 11. So your compression is increased. So here temperature and the pressure will also increase. As it reaches to again TDC, the spark will be given. Here it is called heat addition. So this spark is given. So this petrol which is mixed inside this chamber, it like a blast. It is happening, and a very high pressure. It is compressed like this. So your piston will go down like this. So in this stroke, when it is falling down by the help of the burning gases, that stroke is called the expansion stroke. In the expansion stroke, work is produced by the engine. In this case also, your inlet valve and exhaust valve both will remain closed. Now we have reached again to the BDC, means at the bottom, your both valves are up to now both are closed, but as and when it start upward, your exhaust valve, the red color valve, will open, and the exhaust burned gases will move from the exhaust valve. And as and when it reaches at the top, the exhaust valve is fully open, all gases are out, your exhaust valve will be closed. And as and when it reaches, again it start falling down, inlet valve will open, and in this way whole cycle is completed. And this is repeating again and again and again. Every time in 4 stroke, one will be the power stroke, one will be the suction, one will be the exhaust, and one will be the expansion or the power stroke. So like this, we have the 4 strokes normally. We have the 2 stroke. In this 2 stroke, we don't have the valves, but the piston is designed in such a way that these valves are not required. So we say that only compression stroke and the expansion stroke. Though only 2 strokes are there. But most of the time, nowadays, we have banned the 2-stroke engine because of the pollution, because unburnt gases are very huge in the 2-stroke engine. Due to the non-availability of the valve, some unburnt fuel will also mix with the burnt fuel and it will go as a waste. To avoid that thing, nowadays we use the 4-stroke engine. I think it is very much clear for all the people. If anywhere you have any doubt, you can comment in the comment box. Also, I request to like and subscribe this channel. I will be very grateful if you have any comments or you are not understanding any things, you can discuss with me on that. So, I am going now for some thermodynamic process relationship that will be used in our next series. So, here we have for the adiabatic process. So, we can, and here we have the isochoric. Isochoric means constant volume. Okay, so here we have here ideal gas relation. First law, du is equal to dq. So if the volume is constant, your dw is equal to 0 here. So we know that du is equal to dq minus dw, but this is 0, so du is equal to dq. And here the gas relations are P by T is equal to constant. If you see the PVT, so P1 by T1 is equal to P2 by T2, and change in internal energy, this du is equal to mCV T2 minus T1, and heat transfer, it is dq is equal to mCV T2 minus T1. So heat transfer, because here if you see both are same, so heat transfer and the internal energy will be same and the PdV work will be 0. Just now I have discussed here. So because there is no change of volume, so work done will be 0. Now if you talk about the adiabatic process, because our processes will be adiabatic, isobaric or isochoric. So all the 3 processes I am going to discuss here, so that it will be very easy to understand the AutoCycle or diesel cycle or the dual cycle or any cycle. These relations will be used for the derivation. It is very much essential to understand first this, then we have to go for the derivation for the next topic. So in this case, when we have the adiabatic process, so first law how it is defined, it is dq is equal to Tds is equal to 0. It means no heat interaction. No heat interaction. So dq is equal to Tds is equal to 0. But so if this dq is equal to 0, so this du, if you take the first law, du is equal to Pdv or dh. H is enthalpy. So if it is enthalpy, it is Vdp. Understand this too. If you are finding out, you want to find out the internal energy, use the Pdv. It is like work done. And if you want with the help of enthalpy, then enthalpy will be Vdp. Okay, so these two are different, and we have seen in our Gibbs equation, these all things we have explained. Now, if you see the ideal gas relations, PV to the power K is equal to constant. If you see the PVT relations, so P1 by P2 is equal to V2 by V1 to the power K is equal to T1 by T2 to the power K by K minus 1. So, these relations will be used very much. So, we have to understand that when we talk about the adiabatic, so there will be a gamma or K. So, these relations are very much essential. And how much is the change of internal energy is equal to du mCV T2 minus T1. Change in enthalpy is equal to mCp T2 minus. So, here the difference is this Cv and the Cp. If you want to calculate the enthalpy, you have to use the Cp, and if you want to calculate the internal energy, you have to use the Cv. That much you have, and here is a net heat transfer will be 0. I have just now we have given here dq is equal to 0. Pdv work is equal to Pdv is equal to du is equal to mCv T2 minus T1 and VdP work is equal to VdP is equal to dH mCp T2 minus T1. I hope this is very much clear. And so I will go for the isobaric, that is the constant pressure process. So here we will see the first law is equal to du is equal to dq minus pdv, dH is equal to dq minus vdp is equal to dq. For ideal gas relation, V by T is equal to constant. If you take the PVT relation, so V1 by T1 is equal to V2 by T2. Change in internal energy is equal to du mCv T2 minus T1. Change in enthalpy dH mCp T2 minus T1. Heat transfer is equal to mCp T2 minus T1. So this will be heat transfer here, both. Now, work done PdV is equal to PV final minus V initial. And if you take the PV is equal to nRT, so here work done is equal to nR Tf minus Ti, and the VdP work will be 0 because dP is equal to 0, no change. dP is equal to 0, so VdP work will be 0, but PdV work will be there. So this we have to take care of. Now I will talk about the AutoCycle and introduction. This is the first cycle which were developed, especially used for the petrol engine, and this is also called the spark ignition engine. So an AutoCycle is an idealized thermodynamic cycle that describes the function of a typical spark ignition piston engine that is mostly used for the petrol engine. It is the thermodynamic cycle most commonly found in automobile engines. The AutoCycle is a description of what happens to a gas as it is subjected to change of pressure, temperature, volume, addition of heat, and the removal of heat. So these are the things. So in this process, we will discuss that how the pressure is changing, what is happening. When the temperature is changing, when the volume of this system is changing, when you add the heat, what happens? When you remove the heat, what happens? These all things will be discussed in this cycle, and we can understand by the process how these things are happening, and we will also go with the mathematical description of this cycle. The gas that is subjected to those changes is called the system. So inside the piston, inside this cylinder, this is the cylinder, and this is the piston. This is the piston, and this is the cylinder. So inside this gas, this is called the system. Between the piston and the cylinder, the gas, this is the gas which is trapped, that gas is called the system. The system is defined to be the fluid or gas within the cylinder. The effect will be to produce enough network from the system so as to propel an automobile and its occupants in the environment. So what is the application and what is the effect of this thing? That during the expansion of the piston and the cylinder, the work will be produced, and this work will be used to propel the automobile, your bike, car, truck, buses, aircraft, ships, anything where we can use this work which is produced by this type of system is used to drive the automobile or give some automation for this locomotion for any of the automobile. Now I will discuss about the processes of AutoCycle. So here we can see I have described the two cycles. These are the, one is the PV diagram of this AutoCycle, another is the TS diagram of AutoCycle. So this you can see here, the PV diagram. So in this PV diagram, if you see 0 to 1, the green color, it is a suction stroke. 0 to 1, it is a suction. So 0 to 1, the air is sucked in this, your inlet valve is open. I have discussed this thing. Inlet valve is open. As you reach to this 1, then all valves are closed. Now it is compressed 0 to 1. This 1 to 2. So 1 to 2 is isentropic compression process. So this AutoCycle is the working cycle for spark ignition engine or petrol engine. This cycle also known as the constant volume heat addition engine. So here the heat addition will be at constant volume. So here this is the Q in and this is the Q out. Okay, so here 1 to 2 process is a constant isentropic. So in this TS diagram you can see the isentropic. 1 to 2 is a vertical line. It indicates that there is no change of entropy in this diagram. So this 1 to 2 is a constant entropy or isentropic compression. 2 to 3 is a heat addition. And in this volume is constant, Q is added and here Q is out. So 2 to 3 is isochoric heat addition, means it is at constant volume. Constant volume heat is added. Then 3 to 4 is an isentropic expansion process. Here work is done. So just I will write here work done. In 1 to 2 work given, work in, and here the work out. Okay, so net work is equal to work out minus work in. So this is called W net. Okay, so here 3 to 4 is a expansion, in this work is done, and 4 to 1 is again constant volume or isochoric heat rejection. Here heat is rejected to the surrounding. So the same process you can see here, that 1 to 2 is a isentropic. So 1 to 2 is a vertical line. 2 to 3 is your isochoric heat addition. At a constant volume, heat is added, spark is given. Spark is given in 2 to 3. Then 3 to 4, it is expanding, the gases are expanding. Here also 2 to 3. So here the 2 to 3 isentropic expansion processes are happening, and in 3 to 4 expansion is taking place, work is done, and the 4 to 1 is blue color. This blue color indicates that the heat is rejected and again it has reached to its equilibrium or in the first state. So one whole cycle is completed. This is called the Otto cycle. Now I will go for the deriving of this efficiency of Otto cycle. So here I have drawn the PV diagram. This is the PV diagram, and another one is, this is the TS diagram. So this diagram 1 is a PV diagram and diagram 2 is a TS diagram. So we can see here that the 1 to 2 is a adiabatic isentropic process, isentropic compression. 2 to 3 is a heat is given. 3 to 4 is expansion, work we have got, and 4 to 1 is heat rejection, Q out. So Q in and Q out. If you see here, 1 to 2 is a vertical line, and this vertical line indicates that it is a isentropic compression. 2 to 3 is heat addition, is a huge amount of temperature is increased, pressure is also increased. Here 2 to 3, tremendous amount of pressure is also increased. 3 to 4 is expansion is taking place, and 4 to 1 heat rejection is taking place. So now we will see that, let us find the efficiency of the cycle. Heat interaction only take place in 2, 3 and 4, 1. So heat added during the process 2, 3 is Q23. So this Q23 from here to here at constant volume. So we have to write that MCV T3, this T3 here, T3 minus T2. This is the equation 1, and heat rejected during 4-1. So Q41 is equal to Q out is equal to MCV T4 minus T1. This and this, T4 minus T1. So here it is negative. It means work, this heat is rejected. So now net work done is equal to Q in minus Q out. So by the first law of thermodynamics, using first law of TD. So here you will get Q in minus Q out, and Q in we have taken MCV T3 minus T2 minus MCV T4 minus T1 divided by MCV T3 minus T2. So this MCV is cancelled. Here T3 minus T2 minus T4 minus T1 by T3 minus T2. T3, if you divide it, you will get 1 minus T4 minus T1 divided by T3 minus T2. So we got this equation here. So this is the, so here we can see that there are all the four. This is the T1, T2, T3, T4. Means we need all the four temperature to find out the efficiency. So it is better to relate all to T2, T3, T4 with respect to the T1. So it will be very easy to find the efficiency. So now in the next slide, I am going to discuss about, so we need to simplify the above equation in terms of compression ratio R. It is V1 by V2 and it is also V4 by V3. So if you see here V1 by V2. So this is the V1 and this is the V2. So V1 divided by V2 is equal to V4 divided by V3, and this is called the R, and R is called the compression ratio. And sometimes we write RP also, RC. Okay. So here we got this compression ratio. I think you are understood that V1 is equal to V4 and V2 is equal to V3. So V1 by V2 is equal to V3 by V4 by V3, and this is called the compression ratio. In the previous, we have seen that this efficiency is equal to 1 minus T4 minus T1 by T3 minus T2. So here we will take T1 common. So 1 minus T1 here, T4 by T1 minus 1 divided here we will take the T2 common, we will get T3 by T2 minus 1. So here now we have to relate this temperature with respect to R, that is compression ratio, from the process 1 and 2, that is called the isentropic compression. So we know that in isentropic compression, it is T2 by T1 is equal to V1 by V2 gamma minus 1. So this is R, V1 by V2 is equal to R is equal to gamma minus 1. So here, if you see here, okay, this is the gamma minus 1. So taking the second isentropic expansion, that is the 3-4. So here also we can write that T3 by T4 is equal to V4 by V3, and here also V1 by V2, and this is also gamma minus 1. Okay, here V3 by V4 gamma minus 1, and here also it is gamma minus 1. So here we can see that now this T2 by T1 is equal to gamma R to the power gamma minus 1, and here T3 by T4 is equal to R to the power gamma minus 1. So we can write that T2 by T1 is equal to T3 by T4, or we can further cross multiply. So T4 by T1 is equal to T3 by T2. So in this equation we have the T4 by T1. So this T4 is equal to T3 by T1. So this T4 T1 and this is cancelled. So we got here 1 minus T1 by T2. This we can write 1 minus 1 by T2 by T1. So this T2 by T1, from here we can write that this is the R to the power gamma minus 1. So here we got the efficiency eta is equal to 1 minus 1 by R gamma minus 1. So this is the efficiency equation for the Otto cycle. So the efficiency of the Otto cycle, Otto is equal to 1 minus 1 by RC gamma minus 1. So this is the equation for the finding out efficiency of Otto cycle. And we have discussed that Otto cycle is a spark ignition engine where we use the petrol. So for any petrol engine, let it be for car or for your bike or for any aircraft also. Aircrafts, your propeller, your piston propeller, small aircrafts, they are using the spark ignition engines. In next class, I am going to discuss about the diesel cycle, efficiency of the diesel cycle, mean effective pressure of the diesel cycle. This I am going to discuss in my next class. I am referring my references from the PK Nog, Engineering Thermodynamics from Tata McGraw Hill's 4th edition 2008, Yunus Sengal, Michael A. Ball's Thermodynamics and Engineering Approach, Tata McGraw-Hill's 7th edition. And also, I have taken the pictures and the diagram from this Wikipedia Rankine cycle, which I have shown in my previous diagram. Any questions you are welcome to ask. My email is ydwedi@gmail.com. You are welcome to ask any queries, anything in this email. Also, I request to like and subscribe this channel. If you like, it will be very nice and it will be my appreciation that you have liked. Thank you very much for the joining. I will be very soon. I will come with the diesel cycle. Till then, goodbye. See you.
Like, share and subscribe. Hit the bell icon for more updates.